Alright, so in this video we're going to talk a little bit about density curves. You probably didn't realize it, but I've actually been drawing density curves pretty much since we started this class. Partially because I wanted you to get used to seeing them, and partially because I'm lazy, and I'm not afraid to admit that. So we've already been talking about histograms for a few weeks now as a good way to graphically display the way a set of data is distributed. So here I've drawn two different histograms. Let's assume that they're trying to express the same data set. Now if you notice in the top one, the bins are wider, so there are fewer columns. And then in the second one, the bins are narrower, so of course that means there are more columns. And if you can imagine creating more and more histograms using the same data, but just each time making the bins more and more narrow, you can probably imagine the shape that you would end up getting. And that's basically the idea behind density curves, is that we're creating sort of imaginary histograms that have bins that are extremely narrow, and when you do that, instead of having sort of a jagged outline where the heights of the columns end, you would end up with what we call a density curve, which would be more of a smooth curve, like I've just drawn here. So again, I've been drawing curves like this on the board for the last couple of weeks now, mostly because I was just too lazy to try to draw out the exact histogram, but also so that you would be familiar with what this overall shape is. So that's what a density curve is. So it's an idealized, actually let's go back to this last slide for a second. It's really just an idealized idea, I guess, or concept. I know none of you have taken calculus yet, but you might be sort of familiar with some of the ideas behind calculus, or if you take calculus in the future, you can remember this lesson. Because the idea between a histogram and a density curve is a whole lot like the idea behind an integral in calculus. What an integral is simply if you have some sort of graph of a function. I'm just going to draw you a little sketch up here. So maybe you have some function that looks like, I don't know, this. And maybe you want to find the area underneath the function. What you do when you first start taking calculus is you split up the area underneath that curve into teeny tiny little rectangles. And then to find the area under the curve, you just find the area of each rectangle. Because finding the area of a rectangle, of course, is pretty easy. It's just length times width. And if you notice, those orange rectangles that I drew look a little bit like a histogram. So once you get a little bit more sophisticated in your approach to calculus, you can take what's called the integral, and instead of having to estimate the area underneath your curve with those rectangles that I just drew in, you can actually get the exact area. So it's a little bit like the relationship between a histogram and a density curve. And if you didn't catch any of that, don't worry about it. I promise it won't be on the test. You just need to know in general what a density curve is. And density curves have two properties, and these are the two properties you need to keep in mind. First of all, a density curve always has to be on or above the horizontal axis. So all that means is that there's no such thing as a density curve that would maybe look something like this, where part of it's above the horizontal axis and part of it's below. No such thing. That does not work. Density curves have to be above the axis. The other property of a density curve that's very important to keep in mind is that a density curve has an area of exactly 1 underneath it. A density curve can't have an area of 0.95. That's not good enough. And a density curve also can't have an area underneath it of 1.05. That's way too much. It has to be exactly 1. And there is a reason for that, and as we move along in this chapter, you'll get a sense of what that reason is. So here are a couple of density curves that I've sketched out. Notice the top one on the left is skewed to the left, the top one on the right is skewed to the right, and the bottom one is essentially symmetric, or it should have been if I was a better artist. So again, the only thing, or the only two things that we have to keep in mind in order for these curves to be considered density curves is that first they have to be above the horizontal axis, which of course all three of these curves meet that requirement. And then our other requirement is that the area underneath our curve has to be equal to 1. So let's just go ahead and assume that. So I'm just saying by that this area underneath here, if we took that whole area and were able to add up all the bits of it, then that would be equal to an area of 1. And same for the other two density curves. So as you can see, a density curve can be skewed to either the left or the right. That's perfectly acceptable. But what we're going to see most in this course is the symmetric density curve that you see down on the bottom. And most often, if it's symmetric, you're not going to hear it just called a general density curve. You'll hear it called a normal. Oops, not normal. Normal. If I could spell, that'd be great. So this is a normal curve. And I'm sure you've heard of this before. Maybe you've heard it referred to as a bell curve. But this is a pretty common idea. It just says that instances that are very low on the scale or very high on the scale are uncommon, and then most of the data is going to be somewhere in between your maximum and your minimum. So you'll see this normal curve quite a bit, especially in this chapter. And for right now, that's all we need to talk about density curves. We'll talk about the mean and the median of density curves in the next video.